What if you could turn your roof into a personal power plant? What if you could say goodbye to high electricity bills forever? Today, we're not just dreaming about solar power, we're making it a reality. In this video, I'm going to give you the most comprehensive step-by-step guide to installing an on-grid solar system. We'll cover everything from the smallest screw to the most complex wiring calculation, all to help you save money and go green. This is the definitive guide to solar installation, so let's get building. Section 1: Planning and Components. Before you buy anything, you need a solid plan. First, find out your average monthly energy consumption in kilowatt hours, kWh, from your old bills. This will help you choose the right system size. Next, assess your roof. For a 10 kilowatt system, you'll need about 18 solar panels. To calculate the total roof space required for 18 solar panels, you need to consider not only the panel's individual dimensions, but also the space needed for installation, maintenance, and safety. 1. Panel dimensions. A standard 585-watt monocrystalline solar panel typically measures length 2.278 meters, 2,278 millimeters, width 1.134 meters, 1,134 millimeters, area per panel 2.58 square meters. 2. Basic area calculation. To find the minimum area, you simply multiply the area of one panel by the number of panels. 18 panels times 2.58 square meters per panel equals 46.44 square meters. This is the absolute minimum area required if the panels are laid out with zero space between them. However, in a real-world installation, you need to account for several factors that increase the total required roof space. 3. Practical roof space requirements. A good rule of thumb for residential installations is to add a 15 to 20% buffer to the basic area to account for setbacks. Local fire codes often require a certain distance from the roof's ridge, edges, and chimneys for firefighter access. This can range from 0.5 to 1 meter. Walkways and maintenance space. Installers need clear pathways to safely mount the panels and perform maintenance. This also helps prevent self-shading between rows of panels. Obstructions. The usable roof area must be clear of vents, skylights, and other obstructions. Therefore, a more realistic estimate for the total roof space required would be total roof area 46.44 square meters basic area plus 15 to 20% buffer approximately 53.4 to 55.7 square meters. So for 18 solar panels, you should plan for a clear unobstructed roof area of approximately 55 square meters to ensure a smooth and safe installation. Solar panels. These convert sunlight into DC direct current electricity. Inverter. This is the brain of the system, converting DC power to AC alternating current power for your home and the grid. Mounting structure, the framework that holds your panels. Bi-directional meter. This special meter provided by your utility tracks energy flow both to and from the grid for net metering. Safety devices. A crucial step, you'll need disconnects, breakers, and a grounding system. Section 2: Component sizing and specifications. Let's get into the nitty-gritty. Understanding the specs is key to a safe and efficient system. 1. Solar panel, a standard 585-watt monocrystalline panel. This type of panel is an excellent choice for a high-efficiency system. Maximum power, Pmax, 585 watts maximum power voltage. VMPP, the voltage at which the panel produces its maximum power. This typically ranges from 42 volts to 44 volts. For example, a common value is 43.53 volts. Maximum power current, IMPP, the current at which the panel produces its maximum power. This is typically in the range of 13 amps to 14 amps. A common value is 13.44 amps. Open circuit voltage, VOC, the maximum voltage the panel can produce without any load. This is a critical value for string sizing and is typically around 51 volts to 53 volts. For example, a common value is 52.47 volts. Short circuit current, ISC, the maximum current the panel can produce when the positive and negative terminals are short-circuited. This is used for fuse and wire sizing and is typically in the range of 14 amps to 15 amps. For example, a common value is 14.07 amps. Module efficiency. This measures how well the panel converts sunlight into electricity. Higher wattage panels often have higher efficiency, typically around 22% to 23%. 2 solar inverter. Here are the typical specifications for a 10 kilowatt Deye on-grid inverter. Model numbers like Sun 10KG05 may have slight variations. Deye 10 kilowatt on-grid inverter specifications. 1. DC input PV side max. DC input power 13,000 watts, 13 kilowatts. This allows you to oversize your solar panel array up to 13 kilowatts of panels to ensure maximum output during non-peak sunlight hours. Number of MPPTs. 2. This means the inverter has 2 independent trackers to optimize power from 2 separate solar panel strings or arrays, which is useful for roofs with different orientations or shading issues. Number of strings per MPPT. 1 or 2 C max. DC input voltage 1000 volts. This is the highest voltage the inverter can handle from the solar panels. MPPT voltage range 150 to 850 volts. The inverter operates most efficiently within this voltage range. Your solar panel strings must be sized to stay within this range. Maximum input current per MPPT 13 amps plus 13 amps. This is the maximum current from each solar string the inverter can handle. 2. AC output grid side. Rated AC output power 10,000 watts, 10 kilowatts. This is the maximum amount of power the inverter can deliver to your home and the grid. Maximum AC output power 11,000 VA, 11 kVA. Rated AC output voltage 230 volts single phase or 400 volts three phase. The specific model will be either a single phase or three phase unit, so check which one is right for your grid connection. Rated AC output current 14.5 amps for 400 volts three phase or 43.5 amps for 230 volts single phase. Grid frequency 50 Hz, 60 Hz. Power factor greater than 0.99 adjustable 3. Efficiency and safety max. Efficiency 98.6%. This indicates that very little energy is lost during the DC to AC conversion. 3-string sizing. This is the most important calculation for the DC side. You need to connect your panels in series to match the inverter's voltage range. 1. System overview. Total system size 10.53 kilowatts DC, 18 panels x 585 watts per panel equals 10,530 watts, 10.53 kilowatts. Inverter, Deye 10 kilowatts. On-grid inverter, solar panels, 585 watts, monocrystalline. Key electrical parameters. Panel VMPP approximately 43.53 volts, panel VOC approximately 52.47 volts, panel ISC approximately 14.07 amps, inverter MPPT voltage range 150 to 850 volts, inverter max, DC input voltage 1000 volts, inverter max, input current per MPPT 26 amps. 2. The goal of string sizing. The primary goal of string sizing is to configure your solar panels in series so that the total voltage of each string falls within the inverter's MPPT voltage range 150 to 850 volts for optimal performance. It is also crucial to ensure the voltage never exceeds the inverter's maximum. DC input voltage 1000 volts. Under any conditions, especially during cold weather, as this could damage the inverter. 3. String sizing calculations. We need to calculate the minimum and maximum number of panels that can be placed in a single string. We'll use the open circuit voltage VOEs for the maximum number of panels and the maximum power voltage VMPP for the minimum. A. Calculating the maximum number of panels per string. This calculation is critical for safety and is based on the highest possible voltage the panels can produce, which occurs at the lowest ambient temperature. For this analysis, we will use the standard VOC from the datasheet, assuming a conservative approach without a temperature coefficient. Formula: maximum panels equals inverter max. DC voltage slash panel VOC star calculation 1000 volts slash 52.47 volts, approximately 19.05. You must always round down to the nearest whole number because you cannot have a fraction of a panel. Result: 19 panels per string. A string of 19 panels would have a voltage of 19 times 52.47 volts equals 996.93 volts, which is safely below the 1000 volt limit. B. Calculating the minimum number of panels per string. This calculation ensures the string's voltage is high enough to activate the inverter's MPPT tracking, especially on hot days when panel voltage is lower. Formula: minimum. Panels equals inverter minimum. MPPT voltage / panel. VMPP asterisk. Calculation: 150 volts / 43.5, 3 volts, approximately 3.44. You must always round up to the nearest whole number. Result: 4 panels per string. 4. System configuration and stringing options. You have a total of 18 panels and a Deye inverter with 2 MPPT inputs. Your string size must be between 4 and 19 panels. Based on these numbers, here are the viable configuration options. Option 1, 2 strings of 9 panels each. String 1, 9 panels. String 2, 9 panels. Total panels, 18. String voltage VMPP, 9 panels x 43.53 volts equals 391.77 volts. String voltage VOC, 9 panels times 52.47 volts equals 472.23 volts. Analysis. This configuration is ideal. Both the VMPP and VOC values fall well within the inverter's MPPT range of 150 to 850 volts, ensuring excellent performance. You can connect one string to each of the inverter's 2 MPPT inputs, which is perfect for maximizing efficiency, especially if the panels are on different roof sections or face slight shading. Option 2, 1 string of 18 panels, not recommended. String 1, 18 panels. String voltage, VMPP, 18 panels x 43.53 volts equals 783.54 volts. String voltage, VOC, 18 panels x 52.47 volts equals 944.46 volts. Analysis. While technically within the inverter's limits, it is generally not recommended. If a single panel fails or is shaded, the entire string's output is drastically reduced. Using a single large string also does not utilize the inverter's dual MPPT capability. 5. Conclusion and recommended configuration. For a 10 kilowatt system with 18 times 585 watt panels and a Deye 10 kilowatt inverter, the most effective and reliable configuration is 2 strings of 9 panels each, with each string connected to its own MPPT input on the inverter. This configuration maximizes the efficiency of each panel, utilizes the inverter's dual MPPT inputs, ensures the voltage and current are well within the inverter's operating range, provides redundancy so that if one string's performance is affected, e.g. by temporary shading, the other string continues to produce power at full efficiency. Section 3, DC and AC electrical components. Now let's look inside the electrical boxes. DC distribution board, DCDB. This is where all the DC power from your strings is combined and protected. DC distribution board, DCDB components. The DCDB is a crucial safety component that serves as a central point for DC wiring and protection between your solar panels and the inverter. For a system with 2 strings, it's a vital enclosure that houses the following key components. 1. Fuse. Sizing calculation. The fuse size is calculated based on the maximum current a single string can produce, which is its short circuit current ISC. According to standard electrical codes like the National Electrical Code or IEC, the fuse must be rated for at least 1.25 times the ISC. It's also good practice to use a safety factor of 1.56, which accounts for both the continuous operation and a potential surge from high irradiance. Panel 1SC 14.07A number of strings. 2. Fuse sizing standard rule. Fuse size equals ISC times 1.25. Calculation 14.07A times 1.25 equals 17.59A final fuse size. You must round up to the next standard fuse size. A common size for this current is 20 amps. Specifications. Fuse type, PV rated DC fuse link. Current rating, 20 amps, voltage rating. The fuse must be rated to handle the maximum open circuit voltage, VOC, of the string. For our recommended string of 9 panels, 9 times 52.47 volts equals 472.23 volts. A fuse rated for 1000 volts DC is the standard and safest choice as it provides a generous buffer. Quantity: you will need 2 fuses, one for each of the 2 solar strings. 2. DC isolator switch. Function: the DC isolator is a manual switch used to safely disconnect the solar panel's DC power from the inverter. This is essential for maintenance, troubleshooting, and emergencies. Specifications and calculation: the isolator must be rated to handle both the maximum voltage and the total maximum current of the solar array. Voltage rating: the isolator's voltage rating must be greater than the maximum VOC of the entire array. For your system, this is a single strings VOC, which is 472.23 volts. A standard 1000 volts DC rated isolator is the appropriate and widely available choice. Current rating: the current rating must be greater than the sum of the short circuit currents ISC of all parallel strings. Total ISC 14.07 A per string times 2 strings equals 28.14 A. The isolator's current rating must be greater than this value, a 32 A or 40 A3. Surge protective device, SPD. Function: an SPD is a lightning and surge protection device that protects the inverter and other sensitive components from high voltage spikes, which can be caused by lightning strikes or grid fluctuations. It diverts the excess voltage to the grounding system. Specifications. Type: a Type 2 SPD is standard for residential PV systems to protect against indirect lightning strikes. For regions with high lightning activity, a Type 1+2 SPD may be recommended. Voltage rating: the SPD's maximum continuous operating voltage, UCPV, must be greater than the maximum VOC of the solar array. For your system, a 1000 volt DC rated SPD is the correct specification. Discharge current: the nominal discharge current I sub in and maximum discharge current I sub max indicate the device's ability to handle a surge. Common ratings for solar SPDs are IN of 20 kA and I max of 40 kA. Configuration: the SPD will be a multi-pole device to protect both the positive and negative lines of the strings. AC distribution board: this is where your solar power connects to your home's main electrical panel. The AC distribution board, ACDB, often your main electrical panel, is the final point of connection between your solar inverter and the utility grid. It's where the three-phase AC power generated by the inverter is safely distributed to your home or business. Correctly specifying and installing these components is essential for the system's safety, reliability, and compliance with electrical codes. Component 1. The AC breaker. First up is the AC breaker, and it's all about safety. Think of it like a smart fuse. Its job is to automatically disconnect your solar system from the grid if there's a problem, like an overload or a short circuit. Here's how we size it. For a 3-phase 10,000 watt inverter, we first calculate the maximum continuous output current. Using the formula I equals P divided by voltage multiplied by 1.732 multiplied by PF, where P is 10,000 watts, V is 400 volts, and the power factor is roughly 1, we get a current of about 14.43 amps. Electrical codes are very specific and require that the breaker's rating be at least 125% of that current. So we multiply 14.43 amps by 1.25, which gives us 18.04 amps. Since breakers come in standard sizes, we always round up to the next available size. In this case, that's a 20 amp 3-pole circuit breaker. It's the perfect size to protect all 3 phases of your system. Component 2, the AC isolator. Next, we have the AC isolator. This is your manual emergency switch. It's a physical disconnect that lets you completely shut down the solar inverter from the grid for maintenance or in an emergency. Its specifications are straightforward. It needs to be rated for your system's voltage. So a 400 volt or 415 volt isolator is required. More importantly, its current rating must be equal to or greater than the AC breaker's rating. Since our breaker is 20 amps, we'd choose an isolator with at least a 20 amp rating. But something like a 25 amp or 32 amp is a common choice, providing a great safety buffer. Component 3. The AC surge protective device. Third on our list is the AC surge protective device, or SPD. This is a lightning rod for your inverter. protecting it from sudden voltage spikes that can come from the grid, like those caused by lightning strikes or utility switching. For a three-phase system, you'll want a Type 2 AC/SPD with a three-phase plus neutral configuration. It needs to be rated for a 400-volt system. As a rule of thumb, look for one with a nominal discharge current of at least 20 kiloamperes and a maximum discharge current of 40 kiloamperes. Component 4. Under-over voltage protection relay. Now for one of the smartest parts of the ACDB, the under-over voltage protection relay. This little device constantly monitors the grid voltage. If the voltage gets too high or too low, the relay automatically disconnects the inverter. This is a crucial safety feature that protects your equipment and prevents a dangerous condition known as islanding, where the solar system keeps powering a section of the grid even when the utility is down. It should be a three-phase relay rated for a 400-volt system with an adjustable voltage range to prevent nuisance trips from small fluctuations. Component 5. AC load breakers. The final components are the AC load breakers. While not directly part of the solar system itself, they are critical to the overall panel's safety. These are the standard breakers that protect the individual circuits in your home, like your lights and appliances. When you add a solar breaker to your main panel, you must ensure that the total amperage of the solar breaker and your main breaker doesn't exceed the panel's internal busbar rating. For example, in a 200 amp panel, if you have a 100 amp main breaker and a 20 amp solar breaker, your total is 120 amps, which is well within the 200 amp limit. Section 4. Wiring connections. Now for the grand finale, wiring connection, DC and AC distribution board. Get this right and you've got a safe, efficient system. Get it wrong and, well, don't get it wrong. Let's start with the DC side. DC wiring. From panels to inverter 1. Mount the panels. Start by securing your panels to the mounting structure on the roof. Ensure all bolts are tightened to the manufacturer's specifications. 2. String wiring. Connect your panels in series to form your 2 strings of 9. Connect the positive terminal of the first panel to the negative terminal of the second, and so on. Make sure your MC4 connectors click into place securely. These are key for a weatherproof and reliable connection. 3. Homing the wires. Route the positive and negative cables from each string down to the DC distribution board, DCDB. Use UV-resistant cable ties and clips to secure the cables neatly and safely along the mounting rails and down the side of the house. Always use conduit where the wires are exposed or run through walls to protect them from damage. 4. DCDB connections. Inside the DCDB, connect the positive cable from each string to its designated fuse. The negative cable from each string connects to its corresponding terminal. The output from the fuses and negative terminals then goes to your DC isolator switch. Finally, connect the output of the DC isolator to the inverter's DC input terminals. Remember to connect the positive and negative leads of each string to their own MPPT input, as we discussed earlier. AC wiring from inverter to the grid. This is where your solar power connects to your home's main electrical system. 1. ACDB. Preparation. The inverter's AC output is 3-phase. You'll need to run a 4-core armored cable, or 3-phase plus neutral wire, from the inverter's AC output to the AC distribution board, ACDB, which is often your main electrical panel. 2. Under-over voltage relay. Install the under-over voltage protection relay in the ACDB. This relay is a critical safety device that monitors the grid voltage. Connect the grid's 3-phase and neutral lines to the relay's input terminals. The relay's output will then control the main solar breaker. 3. AC breaker and isolator. Install the 20 amp 3-pole circuit breaker in a spare slot in your ACDB. Also install the 3-phase AC isolator switch. The output from the inverter's AC terminal connects to the input of the AC isolator, and the output of the isolator connects to the breaker. 4. CT sensor installation. The current transformer. CT sensors are small but mighty. Clip the 3 CT sensors onto the main 3-phase service cables coming from your utility meter before they go into your main panel. These sensors measure how much power you're using from the grid. Connect the CT sensor wires to the designated ports on your inverter or monitoring device. This allows your system to monitor both your solar production and your home's consumption. 5. Final connection. Connect the output of your new 20 amp solar breaker to your main busbar. This final connection allows the power from your inverter to flow into your home's electrical system and, when you produce more than you use, back to the grid. Grounding, the foundation of safety. Grounding is non-negotiable. It protects people and equipment from electrical faults and lightning strikes. 1. DC grounding. Every solar panel frame must be connected to a common grounding wire. This wire runs down the roof and connects to the main grounding electrode of the system, usually a copper ground rod, driven deep into the earth. All the metal mounting rails should also be bonded together and connected to this grounding wire. 2. AC grounding. Your inverter has a dedicated grounding terminal. The inverter must be grounded to your home's main electrical panel and the main grounding electrode. Make sure this connection is solid. All metallic enclosures like the DC-DB and the AC-DB must also be properly grounded. Once all the wiring is complete, double-check every connection. A loose wire can be a fire hazard. Use a multimeter to confirm voltages and continuity before you energize the system. Section 5. Final steps and monitoring. Once everything is wired up, you must test the system with a multimeter to ensure all connections are correct. After passing inspection from your local authorities and utility, they'll install your new bi-directional meter and you'll be ready to go. Now, the fun part, monitoring. Use your inverter's smartphone app to track your energy production in real time. It's a powerful tool that shows you exactly how much you are saving. And there you have it, a complete guide to installing your own on-grid solar system. If you found this video helpful, please hit that like button and subscribe for more projects. Let me know in the comments if you're ready to make the switch to solar.